This is SpaceTime Series 29, Episode 45, for broadcast on the 15th of April 2026. Coming up on SpaceTime, the South Atlantic anomaly growing, raising the question of whether planet Earth's magnetic poles are about to flip. A new study narrows down the most likely locations for water on the Moon. And for the first time ever, pairs of atoms have been observed existing in two places at once. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study has confirmed that a giant weak spot in planet Earth's protective magnetic field, known as the South Atlantic Anomaly, is growing ever larger. The findings are based on 11 years of magnetic field measurements by the European Space Agency's SWARM satellite constellation. It shows that the South Atlantic Anomaly has expanded by an area nearly half the size of continental Europe since 2014. And it's all very concerning, because the Earth's magnetic field is vital for life on our planet. It's a complex and dynamic force that protects us both from cosmic radiation as well as charged particles from the Sun. It's largely generated by a global ocean of molten, swirling liquid iron that makes up the Earth's outer core, 3,000 kilometers beneath the planet's crust. This geomagnetic dynamo creates electrical currents, which in turn generate Earth's continuously changing electromagnetic field. But in reality, the process that generates the field is far more complex. And that's where ESA's SWARM comes in. SWARM comprises a constellation of 3 identical satellites that precisely measure magnetic signals that stem from the Earth's core, mantle, crust and oceans, as well as from the planet's ionosphere and magnetosphere. This has allowed scientists to gain more insight into the different sources of Earth's magnetism. It helps them understand how and why the magnetic field is weakening in some places and strengthening in others. The weak field, the South Atlantic Anomaly, was first identified southeast of South America back in the 19th century. Today, the anomaly covers not just large parts of the South Atlantic Ocean, but much of the southern part of the South American continent, as well as Western Africa. The South Atlantic Anomaly is of special interest for space safety. That's because satellites travelling over the region are faced with higher doses of incoming radiation. That can lead to malfunctions or damage to critical hardware and can even cause systems blackouts on spacecraft. In fact, computers aboard the International Space Station often develop issues as the orbiting outpost flies over the anomaly, and astronomers need to turn the Hubble Space Telescope into safety mode whenever its orbit takes it over the area. The new results, reported in the journal Physics of the Earth and Planetary Interiors, reveals that the South Atlantic Anomaly expanded steadily between 2014 and 2025. A region of the Atlantic Ocean southwest of Africa has experienced an even faster weakening of the Earth's magnetic field since 2020. The study's lead author Chris Finlay from the Technical University of Denmark says the South Atlantic Anomaly is not just a single block. It's changing differently towards Africa compared to near South America. He says there's something special happening in this region. It's causing the field to weaken in a more intense way. The behaviour is linked to strange patterns in the magnetic field at the boundary layer between the Earth's liquid outer core and its rocky mantle. These are known as reverse flux patches. Finlay says normally one would expect to see magnetic field lines coming out of the core of the southern hemisphere, but beneath the South Atlantic Anomaly, scientists see unexpected areas where the magnetic field, instead of moving out from the core, is actually travelling in towards the core. Thanks to the SWARM data, scientists can see one of these areas moving westwards over Africa, which is contributing to the weakening of the South Atlantic Anomaly in this region. This latest model of Earth's core-generated magnetic field marks a new milestone for SWARM, which has now provided the longest continuous record of magnetic field measurements from space. The latest SWARM results also show interesting changes in the Northern Hemisphere, highlighting the dynamic nature of Earth's magnetism. SWARM shows one point in the Southern Hemisphere where the magnetic field's especially strong. But in the Northern Hemisphere there are 2 points of high strength, one around Canada, the other around Siberia. Now, Finlay says when you're trying to understand Earth's magnetic field, it's important to remember that it's not just a simple dipole, like a bar magnet. It's only by having satellites like SWARM that scientists can fully map this structure and see how it changes. However, since Swarm has been in orbit, the magnetic field over Siberia has strengthened, while it's weakened over Canada. In fact, the Canadian strong field region has shrunk by about 0.65% of Earth's surface area, which is almost the size of India. At the same time, the Siberian region has grown by 0.42% of Earth's surface area. That's comparable with the size of Greenland. The shift, which is caused by complex processes going on inside the Earth's turbulent core, is associated with the northern magnetic pole moving slowly but steadily towards Siberia over recent years. This shift is important for navigation, which is affected by the dance between the two areas of strong magnetic field. So what does all this mean? Well, we know the Sun flips its magnetic polarity every 11 years. It's part of the Sun's solar cycle. When this happens, the Sun's magnetic north pole suddenly becomes south, and the magnetic south pole has a north polarity. Now, planet Earth does the same thing, but on far longer timescales, often of hundreds of thousands of years. The geologic record shows that reversals appear to occur statistically randomly. There have been at least 183 pole reversals over the last 83 million years, which means on average Earth's magnetic poles reverse polarity roughly every 450,000 years. The problem is the last time this happened was some 780,000 years ago, so we're well overdue for the next. And the last time it happened, we didn't have the electronic technology we have today, and that raises questions about what that means for our civilization. And there are also widely varying estimates as to how quickly these flips occur. Some scientists think the most recent 4 reversals took an average of 7,000 years. Others suggest the duration is dependent on latitude, with shorter durations at lower latitudes and longer ones at mid and higher latitudes. Still others estimate the duration of a full magnetic pole reversal can vary from between 2,000 and 12,000 years, although some reversals may take as long as 70,000 years to complete. And there have also been episodes where the magnetic field has inverted for only a few hundred years. But these are classified as excursions rather than full geomagnetic reversals. It's thought during such an excursion, the magnetic field reverses in the liquid outer core, but not in the solid inner core. Without the Earth's magnetic field to protect us, we could expect far higher doses of radiation. Now, clearly life has survived these events, so it's not going to be completely catastrophic, but it will mean more sunscreen and therefore more slip, slop, slap. This is Space Time. Still to come, a new study narrows down the most likely locations for water on the Moon, and for the first time, pairs of atoms have been observed existing in 2 places at the same time. All that and more still to come on Space Time. A new study suggests water likely accumulated on the Moon slowly over billions of years rather than during one single big event. The findings, reported in the journal Nature Astronomy, will help resolve a lunar mystery which has puzzled scientists for decades. Observations have provided tantalizing hints that water is plentiful on the Moon. It's not pooled on the surface in great oceans, but as ice on the floors deep inside permanently shadowed craters around the Moon's polar regions, areas where sunlight never reaches. But that raises the question, how did the ice get there? And also, why it seems to exist in some of these craters but not others. While the new research can't pin down the exact source, it has allowed astronomers to rule out several hypotheses. Interestingly, the new findings also suggest that the Moon's oldest craters also have the most ice, and that implies that the Moon's been accumulating water more or less continuously for as much as 3 to 3.5 billion years. Now, the reason water on the Moon is so important is because it presents a goldmine for astronomers. See, future manned explorers on the Moon could mine the ice for drinking water, and they can even use it to make rocket fuel by splitting apart the hydrogen and oxygen atoms. The study's lead author, Oded Aronson from the Weizmann Institute of Science in Israel, says finding water beyond Earth in liquid and usable form is one of the most important challenges in astronomy. It's possible that cryovolcanoes in the distant past may have transported water to the lunar surface from deep underground. More likely, however, is that water arrived on the Moon on comets and asteroids, or that it could have been carried there through the solar wind, the constant stream of charged particles flowing out from the Sun. See, these solar wind particles include hydrogen, which could then combine with oxygen in the lunar regolith to form water molecules on the lunar surface. Regardless of where the water came from, scientists are fairly certain the ice is built up in what's known as cold traps. They're craters on the lunar surface that exist in permanently shadowed areas which haven't seen the sun, in some cases, for billions of years. Observations from the Lyman Alpha Mapping Project instrument on board NASA's Lunar Reconnaissance Orbiter, which was launched back in 2009, found evidence of what might be water ice in some of these craters. What's also clear from the observations is that the ice has a patchy distribution. It's not concentrated in the same quantities in every crater, and there's no real explanation for that. Aronson and colleagues wanted to come up with an explanation, and to do so, they hit the rewind button on the Moon's history. They used lunar surface temperature data from the spacecraft's Diviner instrument and a series of computer simulations to estimate the evolution of craters on the lunar surface. But there's a complicating factor. See, the Moon didn't always sit in its current orientation, which we know today. Instead, its tilt relative to the Earth has shifted over time. As a result, craters that are in shadow today may not always have been in shadow. Drawing on their simulations, the authors have come up with a list of Moon cold traps which have been darkest the longest. The Moon's oldest and darkest craters are also where the greatest signs of ice are located. And those findings may give astronomers hints as to where to go looking for water in the future. The Moon's Haworth crater, which sits near the lunar South Pole, for example, has likely been in shadow for more than 3 billion years, so it's going to be a leading candidate for storing lots of ice. Ultimately, the question of the source of the Moon's water will only be resolved by sample analysis. Luckily, NASA are sending people there, and needless to say, we'll keep you informed. This is Space Time. Still to come, for the first time ever, pairs of atoms have been observed existing in two places at the same time. And later in the science report, a new study has shown that King Harold's legendary 200-mile march from York to the Battle of Hastings in 1066 never really happened. All that and more still to come on Space Time. For the first time ever, quantum physicists have observed pairs of atoms entangled in two different places at once. The findings, reported in the journal Nature Communications, used helium atoms, which have mass and so experience gravity, making it all a major advancement over previous experiments which used photons of light and so have no mass. One of the study's authors, Sean Hodgman from the Australian National University, says it's really weird to think that this is how the universe works. He says reading about it all in the textbook's one thing, but it's really strange to think that a particle can exist in two places at once. The development enables new ways to examine one of the biggest unanswered questions in physics. How does the small-scale physics of quantum mechanics interact and mesh with the large cosmic-scale physics of gravity and general relativity? The study's lead author, Yogesh Sridhar, also from ANU, says experimentally it's extremely hard to demonstrate this. Several people have tried in the past to show these effects, but they've always come short. The new findings confirm predictions from over a century ago that matter can really exist in two different locations at once and can interfere with itself even in those separate locations. Hodgman says, by observing quantum entanglement in atoms for the first time, science is a step closer to finding out whether the theory of everything is real or not.
It's really weird for us to think that this is how the universe works. You can read about it in a textbook, but it's really weird to think that a particle can be in two places at once. The fact that we can confirm that and that our work shows that is really quite amazing, that we can show that that's how the universe works. This weird quantum weirdness is actually reality.
It's very hard to wrap your head around what's actually happening. So people sort of allude themselves to science fiction and saying, oh, it can't be true, it can't be real.
We know from our everyday observations of the world that's not how the world works in our everyday experience. And that's why it's really important for labs like us to show that, yes, at the extremely small scale, it indeed does seem to be how the universe works.
Experimentally, it's extremely hard to sort of demonstrate this. Several people, to our knowledge, have tried in the past to sort of show these effects in the actual experiment, and they have always come short.
So we're deep in the depths of the Research School of Physics at the Australian National University, and we're just heading to our lab, which is a couple of levels underground, so we can build it on bedrock because we have a lot of laser beams and we want the laser beams to be nice and stable. It doesn't really look like very much from here. The atoms are too small to see, but we get all the data that comes off here, gets sent to a computer, and then we can analyze it.
If an atom is so small, how can we know anything about it?
So quantum physics essentially describes the universe at the very small scale, or the very cold, or things that are moving very slowly.
So once you come down to that scale, what we sort of know as sort of day-to-day occurrences, sort of the way things work, doesn't really make sense or doesn't really sort of work the same way.
So we study helium atoms. So atoms are the constituent particles that form everything, form the building blocks of everything. We tend to like to think of them classically as these small little billiard balls, but in reality they're not. They have these weird quantum properties. They behave as these speared out fuzzy blobs that are much more like waves.
We try to understand reality and try to see how the world works. And when you start going at sort of these smaller scales, you start asking them more fundamental questions.
Now, the solar system is held together by gravitation.
So gravity describes things on large scale, quantum describes things on small scale. We're not quite sure how you get from small to large scales because they describe things in a very different way. So when quantum theory was first developed, because it came up with these weird predictions, a lot of physicists didn't like these ideas. And one of those physicists included Einstein. Einstein really spent his life working on quantum theory and also relativity, which is the study of gravity, and yet he still couldn't come up with a theory that coherently described both of them, which is called the theory of everything. There are a lot of physicists that are devoting a lot of time on trying to get these two theories to work together and talk to each other, and there are some theories in development. The trick is coming up with experimental tests.
Even though sort of the theory has been established and there have been many tests that have been done to show that the theory is valid, there hasn't been a test to show that the theory is valid when you look into the sort of momentum of atoms.
So this is the start of our experimental sequence here, where we have a cryogenically cooled, so that's using liquid nitrogen to make things extremely cold. We go through a Zeeman slower, which is this copper coil here that slows the atoms down from about 1,000 meters a second to less than 100 meters a second.
So then we have this beam called the push beam that pushes the atoms towards the second chamber.
This is our final science chamber, where we start with our cloud of ultra-cold atoms. We then collide them and generate the entanglement. I started my PhD nearly 20 years ago, working in the same lab that we did the test today. And back then, when we were building parts of the apparatus, it was kind of a long-term goal that we could look at some of these fundamentals of entanglement. It was one of the long-term goals of this apparatus, and it took us nearly 20 years to actually be able to realize it.
That sort of has led us to this point where we can actually run experiments that test these theories, not just in sort of these hidden properties that lie in the atoms, but actually looking at their motion and stuff.
I often joke that our experiment, it's basically like a several $1 million Meccano set that you can sort of put together and play with, and yeah, we're quite privileged to be able to work on. Einstein and a couple of co-authors, Podolsky and Rosen, came up with a paper, the famous spooky action at a distance paper, where they said that two entangled particles, if you measure one, it will instantly affect the properties of another. And now they didn't like that, and they said that this just shows how ridiculous quantum mechanics is, and this can't be the way the universe works. And then another theorist about 30 years later, John Bell, came up with a way to test that mathematically.
In the 1960s, Bell came out with a theorem to sort of test this property, quantum entanglement. And for many years, it was sort of speculated it would be hard to sort of experimentally show this. The recent Nobel Prizes by Alain Aspect, Zellinger, and Clauser, they showed that these sort of experiments can be conducted in the lab.
So most of the Bell tests so far have been done with photons, so with light. A photon is just a small particle of light. But what we've wanted to do is we wanted to extend that into atoms. So atoms are different in that they're particles that have mass, so they're heavy. There's been very few Bell tests on mass, and in particular, there's been no tests where the particles are entangled in momentum. So that's where they move along different paths. And the reason why this is interesting is because you could then extend that to test theories such as gravity. Because the particles have mass, they're also influenced by gravity, and so you could potentially look at entanglement in a gravitational context. What our experiment looks like is, if you take two billiard balls and you collide them off each other, they can either go one way or they can go the other way. Now, quantum mechanically, atoms aren't billiard balls. They're these little funny fuzzy blobs that behave in a very weird way like waves. And so what they do instead is, rather than going this way or that way, they go this way and that way at the same time. And it's only when you make a measurement afterwards that you see an atom here and say, all right, well, now they're here. or you see an atom here. Until you actually make that measurement or do something else to manipulate them, those atoms have gone both directions.
You can think about the driving force in your experiment being the laser beams. If you want to redirect the atom, which are the sort of cue balls in your experiment, to move in a certain direction, to have a certain velocity, you would change that cue stick and the force you would apply in hitting the ball. Being able to create this momentum entangled state requires that we sort of have very good control and understanding of how that laser beam works.
Our experiments are kind of at the opposite end of the spectrum to the Large Hadron Collider. They work on making things extremely fast and extremely high energy, so you can see some really interesting high energy physics. We do the opposite. We work on making things extremely slow and extremely cold, so that when I say collide, and we push the atoms so they collide, they only collide at an extremely slow rate. They're moving at centimeters per second. If you could see them, you'd see them moving extremely slowly. Each experimental cycle takes about 30 seconds, and so we can run several thousand experimental cycles per day if we're running continuously. The data for this result, because we're relying on extremely small coincidences, so we have an extremely low collision rate, it's several weeks worth of continuous data, and that doesn't include all the months of setup time.
It took about a month for us to sort of see this slowly growing signal. And that was been quite exciting, because as the signal was growing, we were sort of anticipating that, oh, we're going to see these results. It was a lot of sort of wary looks. Like we didn't want to sort of count our chicks before they hatch.
It's a pretty important discovery.
I would say it's a big result in the sense that even though sort of the theory has been established and there have been many tests that have been done to show that the theory is valid, there hasn't been a test to show that the theory is valid when you look into the sort of momentum of atoms.
Theoretically, there's nothing super surprising about what we've measured. This is how theoretically we understand the universe to work. But it's one of those things that you need to measure. If we can't measure it, maybe the universe doesn't work the way we think it does. So this result confirms the predictions of over a century ago that matter can be in two locations at once, and it can then interfere with itself even in those locations. Now, in terms of what that actually means, that's still an open area of research. I'm just an experimentalist. I tend to just follow what's called the shut up and calculate approach, which basically says that we know how to describe this with maths in a way that we can predict exactly how our experiments work. Yes, there might be some weirdness, but that's kind of above my pay grade. So one of the big questions is, where does quantum mechanics stop and where does classical physics start? At what point do you stop seeing entanglement? And so that's one of the reasons why it was really key for us to show it with atoms. Many of the technological breakthroughs of the last century have come from understanding the fundamentals of quantum mechanics. And many of the predicted big breakthroughs of the next few decades are also going to come from fundamental quantum mechanics. Now, we don't necessarily know what all those breakthroughs are going to be, but it's through looking at this basic research, through understanding the basics of quantum mechanics, that's where all the best physics inventions have come from.
That's Sean Hodgman and Yogesh Sridhar from the Australian National University. And this is Space Time. And time now to take another brief look at some of the other stories making news in science this week with a science report. And we start by rewriting history. A new study claims King Harold's legendary 200-mile march from York to the Battle of Hastings back in 1066 never really happened. The research by scientists at the University of East Anglia shows that the journey was actually made largely by sea. The findings overturn one of the most iconic stories in English history, altering how the Norman conquest is understood in classrooms, museums, and in the public memory. The study's authors say historians have repeatedly misinterpreted the Anglo-Saxon Chronicle, one of the earliest and most complete written records of English history, which seems to imply that Harold dismissed his fleet in early September 1066, leaving him no choice but to rush his troops south from Stamford Bridge in Yorkshire on foot. It records that the ships came home, a phrase Victorian historians mistakenly interpreted as meaning he disbanded the navy. And so it was this narrative that shaped all later accounts of the Norman conquest. And that's where the new work comes in. It shows that the ships returned to London, their home base, and remained operational throughout the year. In fact, contemporary sources describe Harold sending hundreds of ships to block Duke William after the Norman landing. These references previously caused confusion because historians assumed that Harold had no fleet left. In fact, Harold's so-called missing fleet was used to defend the south coast, then to support his campaign against Harold Hardrada, and finally to rush back south again after the Battle of Stamford Bridge, ready to face Duke William of Normandy. Early accounts describe Harold sending hundreds of ships south after William's landing. So, far from marching south alone, Harold was coordinating a land-sea pincer movement designed to trap the Normans on the Hastings Peninsula. But it seems the fleet most likely arrived too late, costing Harold his archers and his cutting-edge troops, and eventually his life. The new work also revives evidence from a forgotten naval sea engagement which was hinted at in the Doomsday Book. The new interpretation comes as the Bayeux Tapestry is moved to an exhibition at the British Museum later this year. A new study has shown that the world's earliest known octopus fossil wasn't actually an octopus. The findings, reported in the Journal of the Proceedings of the Royal Society B, are based on a fresh examination of Philispia mazanensis, a famous 300-million-year-old fossil long thought to be the world's oldest octopus. To reach their conclusions, the authors used synchrotron imaging to search inside the fossil, finding tiny teeth preserved inside the rock, which prove the fossil isn't that of an octopus, but of an animal related to the modern-day nautilus, a multi-tentacled mollusk with an external shell. The authors say the creature that gave rise to the fossil decomposed for several weeks before it was preserved, and that decomposition was what made it look octopus-like. The findings solve a long-running puzzle in octopus evolution, which had confused scientists for decades, and suggests that octopus actually probably evolved hundreds of million years later than previously thought. A new wave of artificial intelligence hardware is changing how fast large language models respond. Instead of relying only on GPUs, companies like NVIDIA and Grok are pushing different approaches using systems combining GPUs with a new type of chip called an LPU, or Large Processing Unit, designed specifically to run AI models. The new technology works up to some 700 million tokens per second, running up to 350 times faster with 35 times higher throughput. Grok's LPU uses on-chip memory, which avoids delays and responds almost instantaneously. In simple terms, GPUs handle the heavy thinking, while the LPU focuses on responses as fast as possible. This new setup is designed to handle extremely large AI models and long conversations. And while we're on the subject, the artificial intelligence revolution has now progressed to the point where it's become on-device AI. With the details of what that means, we're joined by technology editor Alex Hauer-Voigt from TechAdvice.life.
So Google has launched the Google AI Edge Gallery. That's what it's called. You find it on the iOS App Store and on the Android Store. And it's private, fast, offline AI. It uses something called Gemma 4, Gemma 4. And this is newly released. And this allows you to test the cutting edge of on-device AI. You've got advanced reasoning, logic, and creative capabilities. And you don't have to send the data to a server. It works on your phone and on a Mac if you download the iPhone app to do so. And you can turn off the Wi-Fi and your cellular and you'll get results. So the future of AI, as I've long discussed with you on this program, is on device. So it's private. I mean, in the future, you'll be able to modify the AI to whatever your beliefs are, so that giving you the answers that align with what you believe. But generally speaking, what's available from the AI is excellent. And you can get a 2 billion parameter model, a 4 billion parameter model. The 4 billion one is about nearly 4 gigabytes in size. But that's nothing for most modern phones. And when you download and install the Edge Gallery app, then you can choose which one you want to download. Obviously, download it over Wi-Fi at home or at work or somewhere else, as opposed to your phone data. But then, you've got agent skills. You can chat with AI in thinking mode, the sort of fluid, multi-turn conversations that you're used to. And you've got a step-by-step reasoning process that you see unfolding. So, this is amazing. I mean, it's the future. It's the whole Hitchhiker's Guide to the Galaxy kind of experience. I mean, they never spoke about some sort of a intergalactic internet. The whole book was self-contained, and it popped up whatever information you wanted to know. Earth was mostly harmless, as we famously remember from the Douglas Adams book. So that experience is now real, and it's only going to get better and better and better. And it just means that the future of having robots in your home that will know what to do with first aid, or it'll just learn things much more fluidly and easily. I mean, this is now a reality, and it's free for everyone to try out and use.
It's got to update itself.
Well, look, I'm sure there will be future versions of the library that you can download. Currently, there's a 2 billion parameter model for Gemma 4. There's a 4 billion parameter model. The 2 billion one's about half the size of the 4 billion one. If you've got space and you've got a modern phone, you don't really care. I mean, the standard iPhones come with 256 gigs, so you probably have games or other apps that are taking up more than that space. And so, yes, you'll be able to in future download more and more of these libraries, and there'll be specialized libraries. I mean, there's all sorts of various plugins you can put into this to search Wikipedia, or to ask about an image. You can use multimodal power to identify objects or solve visual puzzles or get detailed descriptions. I mean, there's an audio scribe. This is where you can transcribe and translate voice recordings into text in real time using high-efficiency on-device language models. So, and yes, your iPhone can also translate a voice into text offline, and it's been possible for some time. But until we see the iOS 27 and the Gemini, the Google Gemini-powered Siri enabling the same sorts of things on device natively, you've got third-party programs that can do that, and Google is one of the best AIs out there. I mean, you've got Claude, you've got other things, but most of those have to, as you were saying in the introduction, they have to go to the server to get their answer. If you've got no signal and no Wi-Fi, and you want to talk to AI about virtually anything, you can do it. It's amazing, and it's been long predicted. And look, there have been such on-device AIs before, but they were very small. They were very tiny in comparison. I mean, this is a 4 billion parameter model. I mean, we're talking about cloud AI having far larger databases of information to be able to draw from, but this is still pretty cool, and it's causing big waves. It's only launched in the last week, and so it's worth a shot. It's worth a try. I think you'll download it and like it. It's fun to play with, and the whole AI adventure is absolutely continuing at breakneck speed and pace.
That's technology editor Alex Zaharov-Reutt from techadvice.life. And this is Space Time. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Bytes.com, SoundCloud, YouTube, your favourite podcast download provider, and from SpaceTimeWithStuartGarry.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to SpaceTimeWithStuartGarry.com for full details.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.